Hello. Sorry, I was like coughing up a hairball. Speaking of hair, um, yeah, I just I get bothered when I hear or saw videos talking about determinism, talking about, oh, if you, because everything's made of particles and it's a deterministic type thing, we know the, the way particles interact and whatever else, and if we could predict everything and know everything that is now, trace it backwards, we would be able to know everything that has been, and then was there even a choice? And blah, 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 or something. And my answer to that is a clump of hair on my floor. Yeah, there's no particles moving in that. You can't predict where it was on one moment on the floor, or if I kicked it, or if it was moved around by a gust of wind, or something else, like my fan blowing it around, or whatever. Wherever it landed on the floor, that's where it ended up. And I'll pick it up when I damn well please. However, the thing to notice is you can't predict how that hair ended up somehow magically, if you reversed time, would hover back from the floor through the air towards wherever it was in my head, and then into the mess that is my obviously tangled hair, which I do brush, and then you end up with bits of hair here and there. You can't even see it. It's a tiny amount of hair. But I could have an example of a clump of hair, but my own hair on my head is good enough. And then you'd have to also be able to assume that it's possible from then to figure out where it grew, on which region of my head it came from. And predict the growth pattern of how it reverses its growth all the way back to becoming just a follicle and everything else, and then find out how all of the like vitamins and minerals and whatever else grouped together to become it, and then what did I eat in order to get those vitamins and minerals. Good luck with that. You're never gonna figure it out. So I I get I get bothered when people say about the arrow of time in a video, whatever.
Little Mary May.
I don't care. Shut up. And they say these statements, and I'm like, tracing back the particle, the tracing back particle theory is broken very simply with hair on the floor. You can know where it is, and 2 steps backward. That's a lie. You'll never even know 1 step backward because it's just sitting there on the floor. There's no movement whatsoever. You would not be able to tell if it moved to the left, to the right, if it moved forward towards this end of the floor or the other end behind me or wherever, if it was in my chair at some point and then I pulled it out and then I shoved it on the floor and then eventually I swept it up. You would not know. Also, you wouldn't know the difference of like if it got hot or cold and when that took place. You would just know that some parts of it did get hot possibly, and then cold, and the effects of that, but you wouldn't have any idea when that happened. I didn't say all that, but I said all of this. Until randomly, for no reason, you would ever 10 to the 500 years be able to predict how it gets to the next landing spot on the floor and leaps into my mess of hair and then gets reverse grown into my head to the point where it grew from, just give up. Or go insane thinking you could fully predict anything ever in space. Give up. Because of course space-time wants to tell you that the era of time, thermodynamics, entropy, and blah, and yet it works apparently perfectly fine backwards. Entropy does not work perfectly fine backwards. You can have a starting point, and you cannot have it, like, let's say you have a capsule, and then you pop the balloon, and it fills up the box full of gas. You can't entropy it backwards or whatever with time so that you end up going to the point where you see it unpop the balloon and all of that stuff. And he mentions these things, how the broken egg and it won't unbreak. Well, that means that entropy clearly, or whatever is going on with time, is not reversible. And it's that same thing that as something occurs, it is occurring in a direction of time simply because that's how time works. How does time work? Well, it's weird because time is working on the entire universe simultaneously. Some people would venture to tell you that time is different depending where you are based on gravity or speed of an object. Those people are idiots. They think that they know how time dilates. It doesn't. It just doesn't. I'm making faces and there's nothing to look at. Let's go back to my face for a second. It doesn't. Time doesn't dilate at all. Explain the satellites. Speed and gravity are forces that affect your clocks. Time isn't affected. The clocks are affected. You adjusted for the clocks being affected. That doesn't mean you adjusted for time dilation. You use the fancy word of time dilation because it makes it simplistic. It is all organized. You did the math correctly. You're doing a great job, but you're still misrepresenting what's happening. And when it comes down to it, who cares eventually? Like, when is it going to be important for us to know about how time dilates? Will it ever be important to know how time doesn't dilate at all? The answer is we're not going to need to know how time dilates unless we're trying to perform certain, like, time warping experiments, which the basic of which is to try to make a gravity well. Yeah, make a black hole somehow. And guess what? Miniature, tiny, little atomic-sized black holes have been experimented on. They're not too big of a concern. Apparently, a black hole is simply the fabric of space-time affected by a gravitational force exerting on everything all around the area, but the bubble itself is like an inverse of what is space. It is literally not even a thing. It's not even a thing. Like there's nothing inside the black hole. It it's just it's just a blip. It's like looking at the entire universe and saying, it's weird to say that there's even mass to a black hole because there isn't. It's like, pretend that you have a region of space in the form of a sphere that is simply affected by all other forms of gravity around it and is basically caused by the usual, like, death of a star or some shit. And you end up wondering, wait, hold on. Black hole mergers to become slightly bigger black holes. Well, there's a lot of theories out there. Anyway, the thing about the way that time works, right? There are interactions that all take place, right? But then also you have the idea of um, the next moment. At the very smallest amount of time that could ever be noticed in the universe, you go back and you say the absolute tiniest amount of time, one single instant, and that instant progresses forward somehow. Now you gotta think to yourself, how? How does that happen? How would that look? What would it actually be? Because literally it's the entire universe that is now another one. And this happens at quadrillions of times per second. And the entire universe is re-rendered at the frame rate of quadrillions per second. That's an estimate. That's not an accurate number. Don't quote me on this, but per a quadrillion frames per second is how the universe is done. That's just for a quillion. I shouldn't put a number to the size of that area, but let's say it's like that for every square Planck unit, the tiniest space, and there are quadrillionth of a second instances in every Planck unit of the entire universe. Like we have the reason why I say quadrillion is because of the attosecond. It is this new thing where it's like the fastest known um, interval of, like, forget about light speed, but the speed of the difference between one and another in the form of the frequencies of wavelengths of light that we're sending towards a thing in order to visualize electrons and atoms. This new study and everything is pretty cool. And it's like, it's a billion billion, otherwise known as a quadrillion. So that's why I say that. And it's interesting because isn't light like 300,000 per second or something. Yeah. So now we're on to quadrillions. Frame rates faster than the speed of light itself. You put those two figures together and you're like, wait, duh. Of course you can take the speed of light and like, who cares about it? Just ignore it and look at time. Take a fragment of it and be like, make this fragment last for a year. And that's what they've done. And that's accurate. That's like the tiniest motions of things, because if they can go at that speed, like, you know, you got the slow-mo guys going at like so whatever speeds, and then this amazing new speed thing. And it's like, you think about it, at a quadrillion per second, in every Planck scale unit of the universe. So the same is happening here, the same is happening there, same is happening there. All of these, it's like the entire universe is a bunch of tiny little dots that are all spreading. They're all unified, doing their own things with their interactions. Like the hair is staying together on my face, doing its own whatever thing. The skin cells and everything else are all like elastic and whatever. And it's like, could you ever, by by predicting how materials work, know that I jiggled my cheek skin? You would never know. You'd never know. Determinism broken simply because of yeah, a simple expression. Oh, but we can find out how your brain did stuff and then interpolate from that. That's context clues. That's not you actually knowing stuff based off of what you see here now. These scientists are ridiculous. They make claims that, okay, 2 years ago, they made claims, because that's how old that video is at space time. Well, I made a reaction basically at the same day that that video was out. That channel's gone. This channel's here. Let's listen. So, and of course, you wouldn't, back then, we didn't have the attosecond. We didn't have this atomic scale time length, which is perfect for registering exactly what the hell is happening with electrons going around an atom. What's happening with the quarks inside of the atom and how they're doing their crazy dance. This is the fun stuff about what we are able to notice nowadays. And if you also know about that crazy salt tube that they had a rainbow going through on an angle, it's like, that's cool. I like that. It's really neat. And it's that those two scientists, those two theories about how you can have the tiniest instance of time and this weird salt tube are the exact same thing. It's like visualizing atomic particles and noticing that when you have a polarizer and light and a salt tube, you can get twisty rainbows. And it's like, that's interesting. It's like you think they're not related to each other, but it's the way that the light works and why they are able to have these frequencies that are like exact, and so tiny differences between those frequencies is what makes it possible to have the tiniest instances of time be recordable. I don't actually know how they visually, like with a camera or whatever sensor they're using, to be able to know what the heck happened with the interactions of light on that spectrum, to see things like what the hell's happening with like the atoms of anything. Hydrogen and the little bits on the end of your fingernail and skin cells and blood cells and your eyeball and whatever you want to look at. Like, it's crazy that we can finally say, that the Heisenberg uncertainty principle, pointless now. We know how to predict electrons because we've witnessed how they move, finally, which is what they're going to say in a few months or so. I don't know. I don't care. And like the entire thing about how this eye's looking at you and not this eye. Unless now it is. I like looking with this eye. I don't know why. This one, not this one. Sometimes both. Anyway, time doesn't dilate. Stupid, right? Like you think that time would dilate, but it don't. So like when you go near a black hole, when you go at a certain hyperspeeds and whatever else, like it's weird. One scientist said that that if light could experience something, it was like it was born and then it's now landed on your face. And there it is, dead. It finally took forever. It's like not all light comes from the sun, Some of the light is just from my freaking screen that's pointed to my face, or the light bulb. The sun has nothing to do with it. Not all photons are super, like, 8 minutes old. Some of them are a few seconds old, or an instant old. And they bounce around the room and they make this whole amount of scale of the differences of light and whatever else is happening. And it's not the same light that always existed from the beginning of the universe. It's just it came from a light bulb. The particles in the light bulb came from the universe. Screw you. We're talking about light here that was emitted from something. And it's interesting to know that if light is simply a vibration of the fabric of the universe, then all we have to do is know how to vibrate the fabric of the universe, which we do all the time with the light bulbs that are so basic. But if we knew how to do that without having to use light bulbs, power out of nothing, almost. Ooh. Fun. And the whole idea that you can make quarks out of, like, there was a scientist who said, it may have been Physics Girl, talked about how if you had quarks separated from each other, like a pair of quarks, they would want to make another pair. So if you were able to go into an atom, right, take those free things or whatever amount of things that are in an atom, it doesn't have to be 3. It could be like any number that the total sum equals 3. Like you got positive and negatives, and then the sum of it is all 3, right? That crazy thing that's happening. You take these tiny, most indivisible dots, and you separate them from each other. And the only thing that you would need to do that is use sound. And a sound at a specific frequency, you'd be able to do that. And then suddenly you start at like crazy gigahertz or whatever, something. Probably yada hertz, I don't know. And who cares? Some crazy number of frequency of sound. And specifically sound. Not light, sound is the difference. You get at that frequency and you can jiggle stuff enough that you actually can separate the quarks from each other. And then the thing that would happen is that, well, this one quark wants another pair. So it would make another quark. So you would have now 3 of them. But actually the other one also would want another pair. So you would have 2 pairs of quarks. Now you have 4 quarks just by jiggling the 2 of them apart. Suddenly, boom, you have double the amount of quarks. Jiggle it more and you have even more quarks. 2 times 2 times 2, continuing forever until you have a bunch of hydrogen. And then you want to be careful about how jiggly you make it, because it sets on fire kind of easily. So yeah, you would ignite it, but then you would also try to like clump it somehow. And the best way to do that is inertial. Or specifically you want a gravity well. You want something that pulls it all towards a center point, right? Not magnetism, not magnetism. Don't do that. You'll never get neutrons out of that. Yeah? But if you have gravity, then you can have, but if you have gravity, right? Like, what does it take to make gravity? You just have to speed something up. When you're going, there's no difference between going fast on a thing and going through the space or whatever, blah. You have to realize with centrifugal forces and whatever else, you're pulled back towards the wall kind of fast when that stuff is happening. So that's all you would need. A centrifugal collector. So you have a little jiggly thing, you have a centrifuge, and that would collect all of the stuff coming from the jiggly thing, and you would end up with hydrogen, stable, and you'd want to then fuse that so that, but like you don't want to keep it spinning. You want to have it spin for a bit so it gets away from the center point, which is the jiggly bit, because you want to keep on having them jiggle. Like the original quarks, you want to just keep jiggling those towards and away from each other, so that the other quarks that keep on getting made, they get jiggled separate, and then you get to make more and more pairs constantly. So you have this basic little rain of quarks, which can basically happen with like thousands of times per second. So you're making, with a big enough machine, you can make a lot of hydrogen per second. start filling up a box. And then you can use certain fusion methods and high speed if you want, sort of, to try to clump them together. You don't want to collide them together, but you want to clump them together so that they can get neutrons, because only inertia does that. Only speed will do that. You can't use electromagnetism. Can't. Literally just can't. But you can make neutrons, and then you can be able to make the helium and the hydrogen and helium, the whole things, everything's starting off, and can fuse it to helium free and whatever else, and deuterium and stuff, so you can make more and more stuff eventually. What does this have to do with the arrow of time? I don't know. I'm just telling you how to make matter out of nothing. Why are you questioning this? It's not nothing. It's the vacuum energy of the universe, which is tiny, but still, you can theoretically totally be able to just jiggle something at an extreme amount of frequency with sound. To do that. Um, so, like, if you have one of these reactors on a spaceship, you're not going to run out of rocket fuel. You're not going to run out of oxygen. You're not going to run out of anything, because you'll have the basic building blocks to make stuff. And then in other further down the line reaction systems and organic systems, you can easily just shove all that stuff into a plant or whatever and end up making reactions and whatever that make the stuff that is that you want to do. And organisms like worms and whatever else is really all you need to do the other meat type transformations. And then suddenly you just have everything just pluming like a big old ecosystem. Technically, all you need is, like, you know, a little bit of algae, a little bit of um, bacteria, and then some zooplankton, krill, you know, shrimp, and then eventually goldfish. And then you can have just everyone can eat goldfish for like their entire time there, because they can like cut off a section of the goldfish. And goldfish, if you get them big enough, they can grow to the size of a goddamn lion. Which is like, if you can eat goldfish, then it's like, why would you not just make giant goldfish? I don't understand. Like, why don't you just do that? You know? But in space. In your spaceship. Do that. And then, like, yes, that's my room. What is happening with There are no comments. Cool. Why can I not press the button to revert it back? There it is. Okay, so anyway, it's basically it. I don't know. If you want to think about time, the thing is, and because time doesn't dilate, you have to understand time moves really steady and consistent everywhere. Right? Like, if you really believed, and if you really did the math of what would happen to everything if time were to be moving differently near like the sun versus how it's moving on the planet, then like you gotta do way more calculations and stuff, but you would find out that it just doesn't actually work according to the models. It just can't. Because the thing that happens with time, and it's approximate that the forces of everything going towards a planet or going towards any object moving through space, you gotta realize the entire solar system is moving in an approximate bubble that's around the sun, and it's apparently outside of that bubble is not empty space. It's the nebula, which is all the other gas that's around the Milky Way. It's crazy to think about it, but it's like, wait, what? It's not full of empty space outside of... No, it's a bunch of cosmic rays and stuff. It's a lot fuller out there than us, inside of the solar system, are protected inside of its ejection bubble. Because the sun is just sending out stuff all the time, and the reach of its push, which is interesting to know that the sun's gravity is so powerful it can hold planets together, but the little stuff coming off of the sun is enough to make a big giant ass bubble that forces everything else out, away from the solar system. But us big things, we're attracted to the sun. And the entire the two different layers of debris that's around the sun. It's like, wait, what? Crazy. So it's like, when you try to think about time, the curious thing is what is happening if you were to actually go down to the very tiniest, forget about particles and electrons and all these other things, but you go down to the very tiniest little wobbles that are happening on the picoscales, the energies that are just electromagnetic. Like apparently photon is not anything other than like, what is this weird fluctuation? How does it actually have a frequency? Does it actually in real life look like a frequency that's moving up and down? That this thing has this peaks and troughs and whatever else as it moves through space? As traceable as like this weird wave line? It's like, and it's weird. And like trying to conceptualize the arrow of time is like, it's literally the entirety of space progressing. All at once in a singular direction. The fun part about it is if you really wanted to think of space as a direction, why would you ever think of it as going in only one of two directions? Past and future. why wouldn't you also consider the idea, or have they ever thought about the idea, of what if time went sideways? Huh? Oh yeah, time that doesn't go forwards into the future or backwards into the past, but goes just in its own moment, time adjacent. Well, that's where that's basically multiverse theory. It's time adjacent, time that moves sideways. It's not a forward in time. It's not a backward in time. It's a separate entire instance of time, but it's all to the side a little bit. But of course, if time moves differently based on the orbits of things and gravitational forces of things, then in multiverse, it would also be that there are like crazy things happening. And you realize that, well, what happens if you screw up an orbit? The fabric of space-time, the way that it progressed, it's like you could change, well, the moon was here, but if you literally change it to be over here now because a rocket pushed on it, or something like an asteroid hit it, or whatever else, or you did something to the Earth's rotational spin so that it gives off more energy towards the moon, or less, then you have to also consider what would happen to the fabric of space-time itself for every other side universe. Because they didn't have any of that crap happen. And so you think about the Earth being the same place, but literally, a parallel universe could happen where the Earth is not where it is now, but it could be that it was now somewhere else. And so the funniest thing is that there are enough universes out there in the possible multiverse that you're only going to meet the ones that are near identical to the position of the planet as it is in this universe. Simply moving it in the tiniest fragment in any direction means you cannot access that multiverse ever until you go back in time to the point where it does match. Then you can cross into that other dimension where it had the similarity. What if that never happens? Because the Earth formed at some point, what if some random blip, the tiniest little fragment, in the very beginnings of everything, pushed a tiny packet of gas so that now everything's changed a little bit enough that now the Earth is no longer anywhere near the Milky Way. It could got flung out. Everything else that you can imagine happened in these other universes where other stuff happens. As you describe it, it is happening somewhere in the vast experience of the existence, all existence. The thing about time is that time doesn't need physics to happen in order for time to happen. Time doesn't need physics. Imagine time. Try to imagine time without physics. What would it be like? Well, if you started something out in space, if you start something moving, it really is not going to stop until it gets to wherever it's going. Now, we can say that everything is all moving out in certain directions, and then we also say there's a great attractor and a big flow river of galaxies all flowing towards this great attractor. It's over here somewhere. So that's nuts, and we're in that flow. We, us, the Milky Way, is in that weird great attractor flow that we have noticed as we have mapped the entire universe to say that in this section, yeah, there's a gigantic river of galaxies all going in this one direction, as if the electromagnetic spectrum is so vast and overpowering that the actual eddy currents of this great attractor is enough that it flows all the way through all of the galaxies, reaches us and beyond, and is keep on having everything all pulled in this direction. Some people say that all the galaxies and everything else is all spreading out far away, but it's like, nope, we're going somewhere. A lot of us are going somewhere. There's a lot of us who are spreading out, maybe. It's attenuating as it may be, but if we ever get to the point where we reach the great attractor, we're going to get absorbed into that big ball of fluff. And it's basically, you're going to smack into that black hole. You might circle the drain a little bit if you're lucky, but you're going to smack into that and atomize. We have to get off of this train. We have a few trillion years, don't worry about it. That's the great attractor. It's fun. And the arrow of time says, we're going this way. We could never think of time as reversible, as saying it's perfectly okay to think of time and we're just going away from the great attractor. Because everything is converging towards that thing in this general arc. Similar to how lightning works. Lightning has its own path and weird arc and stuff and channels and whatever, how it works. We are basically on a lightning bolt of cosmic proportions. We are like a dot in a cloud, in a stream that is a lightning bolt. Heading towards a gigantic dot that's like bigger than anything we could ever imagine. And it's going to gulp us. Really far into the future, don't worry about it. So like, Dyson sphere around the sun making a stellar engine to move our solar system out of the Milky Way, out of the path with the great attractor. I mean, we don't even need that much force to do it, and then we'll just be gone, and we'll be into actual interstellar space. True interstellar empty pocket of space, where there's no actual stuff around us, just our own little pocket of solar system, and that's it. Small-minded, take take the entirety of the great attractor flow and use it towards, yeah, why not? Why would we want just our solar system when we can take the entire galaxy with us, or take the entire great attractor and be like, I'm gonna be the thing that's taking all the stuff from everywhere around us in the universe, and be like, this is my pocket now. Why just the solar system? Great question. Genuinely an excellent question. I love that. No, genius. I love it. It's good. Bravo. Come on, you were thinking it. Just why just take the solar system, take the galaxy, take the great attractor itself, take everything else that's in the universe and make a big bang. Because you could. With a great attractor, you could easily go forth and just grab the entire rest of the universe's galaxies and just shove it all into one space. You'd never be able to use all that power. Even a Makashka brain, or whatever the hell name it's called, is like, the brain powerful enough to simulate the universe needs a galaxy. That's all it needs. And now we're talking about the great attractor is the next level beyond that type, whatever, type 6 civilization or some bullshit that they talked about, because we're not even type 1. We can't even use the entirety of our planet, much less our star, much less our solar system, much less the galaxy, much less the cluster of galaxies, much less the great attractor. How many levels was that? Who cares? But you can tell me in the comments. And then the universe. The fun thing about the speed of light in a vacuum is that once you put it into a liquid of some sort, it seems to slow down, but it's actually not. Apparently, people have said that light in a liquid doesn't slow down, but it spreads out. Instead of going woo, 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 it goes woo, but like in a really small area, so it takes longer to move that same distance, but it's still going at crazy energies. It's like someone kicking faster once they're in water instead of running on the air, because they're still wanting to go there. It'll take longer for them to get there, but you understand, effectively, towards everyone else noticing it, light started to move from here to there at a slower rate because it went through water. Guess what? If you speed up the water, maybe you can speed up the light. If you start the water flowing in the direction that the light is flowing, the opposite from, flowing from, light's going this way, water's going that way, could you slow down light even more? Or would it speed it up? Good question. Excellent question. I love that. That is brilliant. Could you do that? The answer is, if the water is flowing towards the light, it means it has more stuff to react to. So technically, that should speed up the speed of light instead of slowing it down. So light, if it was going the same direction as the object that it's moving through, would slow down Question mark? Oh, what? Clearly not. Clearly not. That can't be it. It can't be how it works. Because if you have something going significantly fast enough in the direction opposite of the direction of light's path, it should slow down enough that you see a ball of light just sitting there. It's not moving forward towards my face. It's like a it's like this tiny little extremely bright for some reason. Would it be bright? That's the question, because you're not even seeing light. When you're seeing light, you usually see everything that it's reflecting off of, but it's going through the medium, and therefore, if you actually speed up time or focus on how it moves through the medium, then the reflections and everything else is all like woo, 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 woo. In reality, light is like a vibration, like a sound. Light is sound on the electromagnetic spectrum. Groovy. So I did just take a picture. Um, if you could, the point is, if you could speed up, did it just say that it looks like my eyes something? Shut the fuck up. What does it matter about my eyes? It looks like your eyes aren't like shush. Stop. It's a program saying it looks like my eyes are doing something. I'm like, I don't care. Both of your eyes aren't facing the camera. Yeah, well, that's their rest state. I don't know how to tell you. It's just how they are. Hmm? Okay, whatever. Um, Arrow of time. So you got this whole idea with time. You want to go backwards in time, or you want to go and skip or fast forward yourself so that you not aging, but you end up in a time that has yet to be. Put it that way. Um, what did I just do? What- Who could have predicted that would happen? Eh? Trace back the particles and find out when that happened. You will never know. It's impossible to tell. It really is. Even analyzing your brain, it's like, would you know all this stuff? Never be able to know. Arrow of time. Naturally, when you have um, if the nature of time is possibly at the very basic level, electromagnetic in some form? Maybe? Then you'd have to think that time is moving at a certain rate within the great attractor itself pathway. And therefore, all of time that's happening of the separate entities which are all attracting towards this point, it's all of this. Nothing much is happening out here in the empty spots, and then you have this sudden lightning bolt with all these different arcs all heading towards the stream, all heading towards, with just basic fluid dynamics of how it works, this whole eddy current thing happening, right, of the great attractor. And it's like we can tell where that is and all of this stuff. You can look it up yourself. Great attractor. It's a great video. Done by Veritasium perhaps, or other people, and they talk about it, and it's neat to see. And like genuinely, what is going on? Genuinely. Arrow of time. So if let's say that the fundamental dynamic of time works on the electromagnetic spectrum, right? Could it? Answer to that is ironically no. The arrow of time has to work on a level more specific than the electromagnetic spectrum, tinier than energy itself. It's like you think of the electrons and protons and neutrons and quarks as being these tiniest things, well, the electrons and the quarks being the tiniest things in space, and then you think of the electromagnetic spectrum and the sea of that. And that is like another, like, it's another or 3 orders of magnitude smaller easily to get to just the area of the electron, just the edge of it and its radius to start being flat, right? And then you have to go even deeper and smaller and tinier than that. Because electrons are something. They do have something to them. They are point-like. But there's a structure to them, is the thing. Oh yeah, quantum entanglement is fake. There is no such thing as quantum entanglement. There is causality stuff that happens. There is similarities. There is, ironically, there is hidden variables. It's called, if you split something down to half, then whatever is affecting it on the one half, the tiniest amount of energies could be pushing it on one side, and it'll continuously do whatever it was doing when it got divided. So it will have that spin going this way. The other half will have the spin going the other way. Ironically, they don't see any difference between what they're doing. Technically, if you rotate it 180 degrees, would they be spinning in the same direction? Oh, yes, they would. Now that's crazy. That's ridiculous, and Nobel Prize for that. Because if you take the if you take the half the photon, right, send it one way, and we assume if you know the up spin of that, then you don't, the other one has to have the down spin, right? That's what they say. That is what they say. But if you take that and you 180 it, it's the exact same structure, the exact same action, right? Which means that the photon is actually a structure. It's actually a semicircle that once you divided it, that semicircle has its one format going in one way, and the other circle is going the other direction, and it's doing the exact same thing. That's because if you really looked at a photon, it would probably be a curlicue, some kind of twisty, spinning corkscrew. Originally, it was going this way, right? And then it hits like a salt crystal or whatever the hell it is, or was it calcium? And then it exactly divides in half. One goes in the one direction, one goes in the other direction. They both go to detectors that are exact distances away from that split point, so that they are trying to tell its right or left-handedness, as they call it. And they're like, yeah, if you notice this one has a right-handedness, that one has a left-handedness. Great. So we established that they both have some kind of geometry about them. And it's just crazy to think that if you totally 180 it, yeah, they look identical. Guarantee you they would look identical. And it would be a weird spirally thing. Why? Why would a photon be a spirally thing? And why would it make sense that it's a spirally thing when it's cut in half? And then suddenly that is doing its own thing. Because if it's spirally, right, the spiral is going in this direction. So if you cut a spiral that's going in this direction down the middle, then what do you end up with? You end up with some weird shape that's like it's flat, and then the other end, it has its specific thing going on with like a curl. It's like if you take a screw and you cut it down the middle of the length of the screw, right? That's what a photon is. It's just a little ball shape with a screw curlicue. It's just like a baseball. It's exactly a baseball. Baseballs are just yin yangs in three-dimensional shape, which is ironic. And then you take that shape, but you think of it as a photon, you cut it in half. No matter where it is, it all has the same symmetry. The lines of it are the direction that it will go in, or the right or left-handedness, that if you put them back together, they look exactly stuff. Is there a way you can cut a baseball in half where it doesn't have symmetry? The answer is no. Just a blind, possibly complete lie. No. But what if you cut it so that your cut is close to the end of the curl on that baseball? The baseball look like? I don't have a baseball on me, ironically. I don't even have like a squishy baseball somewhere. I have a soccer ball, not a baseball. But anyhow, if you think of a photon as a baseball, you're pretty correct. They might look like that. Still, yeah. It's an interesting question if you cut a baseball in half in any direction that it's going, like in any orientation of the baseball, like would it always be symmetrical? Both halves. If you flip it over 180, it will look exactly like the other half. Now, I can't help but think that it must be true. It must be at least majoritively true. Like, unless you go on to the highest resolution of what is going on in the baseball, but like, let's just say the lines on the baseball and the overall shape. Would that ever not be symmetrical? And I can't help but think it must be. Anyway, somehow, if you cut it like exactly in half, right? So knowing that there's a right-handed and a left-handed side of the baseball's shaped photon, um, determining that at the detectors, and if you look at one side, then you automatically also know about the other side. It's like knowing that one right-handed glove and a left-handed glove separated and both went to the detectors, and it's like, yeah, you know that that happened. Does that mean causality? No. Did they prove causality? They did not. Nobel Prize for proving causality, and they faked it. And the idiots who gave them the Nobel Prize believed it. That's a that's a hot take. Calling the people who give out Nobel Prizes idiots. I don't care because it's true. They're idiots. But there's only so much that people can learn when in the guise of in the mind frame of the people doing the scientific experiments, the scrutiny and everything else, the stupid idea that people can actually, in a coordinated collective, believe in determinism and the lack of free will because determinism is possible? Maybe? Even maybe. But no, they say some people actually say that determinism is full truth, and I broke that with hair. Hair on the ground. Forget about hair. Think about the tiles on the ground. Think about the paint on the wall. Think about the bricks and the mortar and all of that stuff. What box were these tiles in? Can you go back and use your program to determine atomic jiggles and find out which box these tiles were in? What truck shipped them to this building so that they could be put into place and become my floor? You cannot. You can't. There's no amount of computing that can ever figure that out. What year they were installed in? No way. That's not even possible to get even close because it's a stationary object. And that's the thing about if you talk about objects that are generally, yeah, if you determine the motion of stuff and everything's deterministic, blah, 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 sure, if you talk about motion stuff, but the universe is the gigantic portion of it is freaking static. It's not moving. My chair is 99% not moving, right? It moved a little bit. Wow. Could you ever tell when that happened, if that happened? No. There's no way to tell when it did that or this. You'd never know. Determinism is thrown out the window with my hair. Not like I throw window in the hair. I throw window in the I throw the window in the garbage. The window belongs in the garbage. You can't see out anymore. You have to look at a wall. Seriously though, determinism was a stupid idea that no one with if you think of everything as moving and trajectories, sure. That's a gigantic assumption that's immediately broken by tiles on the floor and hair. And anything else that's it's a static object. All of this stuff isn't moving. None of it has ever moved. This green that you're looking at hasn't moved. Chemical reactions have happened inside of the screen. There's nothing happening to the particles that are making up the glass, the metal around it. The circuitry inside of it is all one giant thing that has always been the way that it always will be. Except for the electrons, which are moving around. That's it. Everything else is stationary, not moving, ever. The teeth are stationary. They're not wiggling back and forth in my face. My bones are basically stationary. My hair, for the length that it is and whatever else, and moving all around, relative to all of that, the hair is basically stationary, as it just sits on my head and stays at the same length. It doesn't elastically go crazy. It's basically, for the floppiness that it is, it's actually quite rigid. It has a tensile strength. It doesn't want to keep on stretching and pulling in one direction. It has a give to it. And when at that point of the contact of my head, it will give, or the strands themselves can break apart and I can snap it in half, into parts. I can cut it into bits. Or I could pluck it from my face. But other than that, stationary. This mustache ain't moving. The muscles move around and the stuff and whatever else, but the hairs themselves, they're not doing a damn thing. So you can't track their trajectory. You can't even. It's just silly. It's just silly that people think that you can do these things, and that determinism was ever possible. And even in a world where there is determinism, where everything that could happen will definitely happen in a specific single way, like hindsight, yeah, you can think of everything that has happened, and it will never happen any other way. It just happened one way. We know this to be true because we've documented it. So therefore, we can determine that it definitely happened this way. This sentence can only happen in one direction in my favor, and all of that bizzle is it is what it is. It could never be anything else. Watching this video over, you can go backwards and forwards and play it forwards, play it backwards, rewind parts of it, jump through parts of it, whatever else you want to do with the frame of reference of the time of the recording of it. And yeah, when it comes to recordings, yeah, you can totally say, oh, I pressed rewind. I saw it moving backwards. It makes sense that it would move backwards. But then you got like the dog running on the beach, and it clearly does not do that backwards often, ever. Dog running on the beach, it always goes forward. Why would a dog running on the beach ever go backwards? It's like, yeah, if it's backing up. It does a totally different leg motions when it's backing up. dog backing up run backwards does not look like a dog moving forwards. It looks like a dog that was backing up that you ran reverse, which is also very weird to look at. It's very weird to see a backing up dog and then you reverse it so it's actually moving, looks like it's moving forward, but you know those like motions that are not, no. That's cursed. Someone make that into a thing. I want to see a reverse backing up dog or cat, anything. People's too boring? People is too boring. Pretty much. Because we basically just go, what's the difference? Who knows? Nothing. No, absolutely no difference whatsoever. Once we start running, then it becomes a thing that you can notice about it. But you can go backwards and it's like, it doesn't really seem to be that different. What is this? Oh, I can do that. I didn't know I could be readily exposed. That's cool. Neat. Annoying, but also cool. Time. Year of arrow. It's interesting that eyes definitely move up and down the same way. You don't find eyes usually ever moving like derpy, which is where the up and down also do weird things. Because like, tilt your head and sure, you can see it going like that and like this. But the other eye is definitely moving up relative to everything else, but it's just because it's sideways and whatever else. And then suddenly when my head is straight up, it looks like it's moved extra far to that side. And sideways is normal looking. And then here it's like, no, it's definitely looking over there more. It's like, how does that work? I don't know. Am I looking at you more when I'm sideways? Should a video always be like this? You would think I'm always looking at you, but this is involuntary, and ironically, this is reality. But this is also reality. How does my brain do this? I don't know. Why is this normal now? Looking, and this is totally not, because the side is looking to that side. Who cares? Arrow of time. So the arrow of time is like, if the arrow of time is a thing, right, that we can manipulate by simple gravity stuff. Like I said, you have to think of if you think of multiverse, right? How can we prove that we're in a multiverse versus not in a multiverse? Well, there's a universe where the North Pole, like up at the top part of the globe, is in the middle. And so if we were to, it's possible to traverse to that, but then you would be like, I'm in the ocean, but I'm experiencing stuff that's related to what would be expected to have happened on the North or South Poles. That's not happening in this universe. It's happening in a different parallel universe where it's like it's similar, but similar enough. And the problem is with the way that tectonic shift happens, like the entire shape of the planet is changing. In other words, you can only get planets that tectonically shift and change, and if you change what's happening to the planet based off of the materials that are deposited into the soil over the course of thousands of years, then the stuff that happened to your planet will have a different tectonic shift adjustments based off of the buoyancy of those objects in the soil as they move through the tectonic plates and all of that jazz. And so you got the stuff that's moving up and the stuff that's moving down, and all the stuff that's moving all over the place, and the way that the continents form would be totally different versus a different parallel universe Earth. So we might still have Canada, but like everywhere else is Pangea. All one big continent. It's like, it's mostly Gia. We are the Pan. And the Pan still looks like Canada. But everything else is Gia. Right? There's a universe where that's a thing. Every type of continental structuring where it's like, oh, you want to make the tallest structure in the universe? Well, just squish everything of the continents all together so you get a mountain that's so big. You can literally just do that. You could just just like a ball of clay, you just squish it, you just pull it all into one spot, you make the biggest mountain that could ever be, and then it will crush itself, and you will still end up with a mountain that goes out into space. Yeah, you will. Yeah, you will. Okay, well then dig deeper into the freaking planet and then pull it all together on one side. And then you got this weird wobbly contour-wampus planet, but who cares? You can get out into space. You can just walk out into space up on the top of that mountain, which at this point makes the Earth look more like a comet, and it would be spinning so weirdly. It'd be very cold. Ironically, the core of the planet would be not a core, but a cone. How many cone-shaped Earths? Does anyone believe in cone-shaped Earth? Screw flat Earths, cone-shaped. Whereas a flat Earth, but then there's a cone on the other side. You know that's possible because all you need is a comet. The cone part is the tail of the comet, and everything is going so fast because of gravity and stuff, moving through the galaxy and the solar system around the sun, that you get a cone-shaped planet. Why not? Everything else is dragging behind. It'd be a teardrop shape. Okay, but let's say it's not. Let's say that the teardrop on the front of it is like really hard, bombarded by cosmic rays till it becomes a cone. Suddenly, flat Earth is no longer impossible. It's not only possible, but underneath it is a cone. Have you ever been to the other side of the cone? Do you know that cones have horizons? No one has ever talked about the cone-shaped planet. It's despicable. It's a possible likely scenario of a planet. With the right situation, it could have happened. It's very unlikely. It is not unlikely. Because one of the things that happens with planets is, and their orbits around other stuff, um, is the tidally locked planet with its moon and all of that jazz. So if you have tidally locked, you are constantly bombarded on one side. That side could flatten out, and then the other side is a cone because it's all pushed towards the back, right? Why don't we see tidally locked places be more cone-shaped planets? They gotta be tidally locked planets have got to be cone-shaped if they're exceptionally close to the planet, the star itself. It can't stay round, being eroded constantly towards one direction, and like it would turn into a cone shape. Why would it not? Right? It's it's an interesting thing thinking about the era of time because, like you say, on the fundamental level, we're talking about 4 quadrillion parts per second is able to be encoded in our universe. That's faster than the speed of light, but we can also witness that happening. And so increase the thingamabob further, even more beyond. Just start playing this video at like 0.25 speed, 0.25 speed, and then suddenly you got everything going like at 4 times the FPS. In reality versus what you're seeing, you know. It's like you can slow it down further. You can always slow it down further, but like this tiny stuff, and it's at these frequencies we're going to start making quarks. Doing these experiments, we are going to start imaging stuff and we're going to start making matter. Guaranteed. It has to start, it has to eventually just start happening, that we're ripping apart atoms with these frequencies and we're going to start making matter. And then the energy crisis is going to be gone because we're just going to have infinite anything that we want to make power. It's not even a question, it's just going to happen. We've already done the experiments, we just can't easily do it. Now we have the means to easily do it, and so it's going to happen. It's like the idea of anti-gravity. It's simply what happens to literally any steam. You wiggle it enough, and it starts just bouncing off of everything else that just wants to be pulled down by the force of gravity, 98 meters per second, whatever And it's like, no, I'm just gonna bounce off of all of you guys who are going down. I'm gonna go up. I'm just going up. I am steam. And the sun makes everything go up so high that we have clouds up there and stuff. And as we move closer to the sun near July, no, we move closer to the sun during January. Look that up. That's fun. We move closer to the sun during January at winter. And so we're getting more energy from the sun. The moisture in the air is able to rise up high enough that it's actually able to reach the area of space, the area of the atmosphere which is cold enough to turn it into ice and snow, and we end up with snow. That's why we have winter. It's part of why we have winter. Ironically, someone else said, "Oh, but it's also based on the way that the orbit and the wobbling of the." Yes, both factors are in play. Both factors are part of what is happening. They both coincide with what is happening. And if you add it all together, you understand that dimmer sun means more stored heat because less winter. And that's a correlation that was made on a video, and I made a comment on it, and I had a 4-week argument with someone about it because he didn't understand how freaking weather works. I was like, seriously, all you have to do is notice in this video, they even say, hey, we're closer to the sun in January, farther away from the sun in July. This happens every year. This is not something that happens over the course of 1,000 years. This is every year we go through this orbit, nearer and closer to the sun. It's crazy. Every year. So it's like, huh, that's neat. Is that not what is happening? Yeah. He literally said we're closer to the sun in January and we're farther away from the sun in July. That's still blowing my mind. It's every year that's happening. Sun is here. We are like woo, 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 woo. The sun is always nearby on that January part. What? That's as much as that's an unintuitive thing. Like you wouldn't expect that to be the truth. You would think we would be closer during summer, right? Because it's hotter, more sun, hotter, right? But no, it's the opposite way. But then also the ironic thing is that the seasons happen with the angle of our planet versus the direction of the sunlight. So when it's straight up, right, you get the winter on the other end. When it's this way, it's like it only goes this much. It only goes like from here to here, here to here, here to here. That's how it wobbles. It's an interesting thing that it wobbles like that. But that's how it's going. It's a very interesting three-dimensional wobble. It's like that. That's how the Earth's moving all the time. This is what you're doing right now. Just really slowly so you don't actually see it or notice it or think about it or feel it, but this is happening. This is you. in the course of 1 year. It's like, whoa, whoa. It's like, that's how the planet works? It's like, yep, crazy. It's like, what would really be stopping us from going, instead of like up here, why isn't it just this way? And what would happen if we were going that way? Well, it would be a lot more consistent. So the sun and everything else affecting us would be like so consistent that we would not have seasons as much. Clearly that is the case. But I'm telling you, the fact that we're closer during January is still an important factor. You can't just ignore that. Farther away in July. Meaning also, if you think about it, right, the more sun that we're getting in January means hotter equals, for us, winter. If that also correlates to, if we notice the sun itself getting dimmer, that means the whole planet is going to experience less winter. And therefore, the whole thing is going to get hotter. The inverse correlation thing. That's crazy, but that's the reality we're living in. And we're putting it all up to greenhouse gases. Greenhouse gases is not as big of a contributor as we say it is. It's played up. It is some, but it's not all of the picture. We also have to consider the brightness of the sun and if our orbit has gotten extra close or extra far away compared to where it has been for the past 100 years. You know, if at the closest point that we end up being extra close back then during the winters, and now we're moving actually further away, or is it that the farther away part is moving closer, so we're getting more and more hot? Could that be what ends up happening to our orbit eventually? As you would think that an orbit that is an egg shape would eventually, possibly in the course of time, turn more into a circle. So would we end up with more winter everywhere? Because we would always be closer to the sun. Even if it goes dimmer. But then what if it starts to brighten up again? Well, then we get an entire age of summer. That's why we can get an ice age. That's why we can get a summer age where everything's on fire, everything's cold for a very long time. Right? It's crazy, but that's reality. And this one guy I was talking to on this comment section was like, for weeks, talking to me about, no, you must have English as your second language because you don't understand this basic concept. I'm like, I'm watching the video, I'm putting stuff together, and before he even said the part about the orbits, I remember seeing a video about the orbits. And the thing is, I'm remembering when I first saw the video. And this is my reaction now because I have a new channel and I have to make the reaction now. Again. So it's actually out there at all. And so I'm having this memory of, hey, it's closer that there's this heat trend of the brightness of the sun seems to correlate with the amount of heat in the planet, and then the heat goes up and the brightness goes down. But then he says about how we're closer to the sun in January and my head explodes, correlates those two objects, put those together, and is like, wait, no, they're inversely correlated, which means when it's going up and we're getting hotter, it's actually getting dimmer with the sun is a correlation, and it's not freaking out. And if you actually put it all together, does that mean that the CO2 is like, does that it completely, absolutely, not 100%, but it absolutely changes the amount of contribute the CO2 is doing. Oh yeah, CO2 is happening all over the place. We got hidden caves that are melting and releasing CO2 and stuff into the air. Which altogether, if you have enough plants, you're just going to get more oxygen, which means more oxygen, ozone and stuff. And literally, guess what? The entire atmosphere is eking off of the planet. We are a comet. You're riding a comet. It's just so big that you don't think of the Earth as a comet because the particles of it that are eking off are such a very small fraction of the actual visible stuff. But trust me on this, planet Earth is a comet. We got to start scooping that gas up and pulling it back into the Earth so we stop losing all of that gas. All of it is just eking out into outer space. It's just floating off. Gravity's not enough to hold that crap in there. Oh, hell no, we're eking off atmosphere. It's nuts. Does that explain hailstorms because it's flowing back down from outer space? No. No. Hailstorms are not because of the outer space. They're still in the atmosphere. They're just extremely high, but they're still in the atmosphere. I'm talking about we're actually leaving stuff, oh, and it's just behind us now. It's gone. We are losing atmosphere. By how much of a percent of the atmosphere is actually leaving? I think it's like one. If you take a meter of upper atmosphere, we are losing 1/1000th of that or something blah per unit of time, which multiplied by the entire volume of the planet is actually a few tons per unit of time. And I don't know about you, but losing a Mount Everest of atmosphere every unit of time, no matter what unit that time is, if it's over a course of a second, a day, a year, 1,000 years, that's atmosphere, that's mass off the planet that we are just losing. Give me some more cosmic rays, please. I want them to absorb into the planet so we have more stuff to have on the planet. That we solidify and reconfigure into the stuff that we need to keep this planet from, totally evaporating into a lifeless rock. Thank you. Kind of embarrassing. I don't want to be an icky planet. No, I don't want to be a gassy planet. I want to be a solid atmosphere planet. As solid as you can be, as every like few kilometers up you go, it gets thinner. But I mean, solid. Until you get to the ocean, then it's like really solid. even though it's wavy, it's a lot more solid than air. And then you get to the rock, and then it's like extra solid. Then you get to the magma underneath that rock, and then it's like it's hot, but it's still solid. Then you get into the core with the iron nickel core of the planet, and it's like, ooh, super dense. How much of the core can we remove from the planet before it starts being bad? The answer might surprise you. Um, I would say 1% before it starts being bad. It's possible that you could have 1% of the core of the planet, which you gotta admit, it's a big core. So if we were to rip that out of there at like we're talking about the size of the entirety of Russia in if you made it like a foot thick of planet core. That's a Fermi estimate if I ever saw one. And like the entirety of that entire like continent covered in a foot of core of the planet. That's a lot of nickel iron that we can pull out without it being bad. Okay, what if it's 1/10 of that? That's still a big amount of core planet. Does that mean we want to be digging down there? You're never gonna get down there. We might be able to house a sun inside of a plasma, whatever else, and of course it's eking out freaking. Did you know? Did you know? Tokamak reactors with their neutrons spitting out is basically an analog to black holes and Hawking radiation. Yeah. The magnetic forces hold everything else in, and the neutrons just want to fuck off. I don't care how powerful your electromagnetic forces and gravity is, the neutrons just want to be like, oh, you're trying to electromagnetically hold me in. I ain't got no charge. I'm out of here. And they zoop and they hit the damn. Now they got a blanket on the thing to pick those up, and they're trying to get the heat off the blanket instead of the molten hot thing, which is the gas itself. If you can't use the entirety of your pop rock or sparkler, and you're just using the heat from the embers that hit your clothing from the sparkler or your skin or your hair or whatever, the little tiny sparks from the sparkler is what you're trying to use to make power. You're burning a whole sparkler. Instead of using the heat from the sparkler, you're trying to get the... No! That's stupid. Stop burning a whole sparkler to try to gain power from your... The sparkler is... It's an... It's a... What do you call it? Represents what it is to be a tokamak reactor and its super high temperatures, right? And the bullshit that is the super high temperatures of the thing. I need to charge my phone eventually. Eventually. Not yet. Yeah, look at hentai. Who cares? Um, yeah, Hawking radiation is simulated by the neutrons flowing out of a tokamak reactor. Yeah. Multiply that but in from the size of, imagine the amount of material. And then you also think of the jet stream that's like the basically a quasar is a black hole that's like eking out. And it's also lit up everywhere because the entirety of what's going around the accretion disk is so bright that it looks like a star. No, wait, that actually is a star. Practically is a quasar. And it's like its electromagnetic plume is just constantly eking out so much stream because it has tons of actual matter around it. But the black hole itself, that's in the center, which there is a black hole inside, there is a black hole inside of a quasar. I'm not wrong about that. I don't care how far you have to zoom in to find the black hole. You're going to find it. It's there. But the mass is so big and it's eking out so much at a time. It's just sending out these jet streams at extreme velocities. As when you think about it, as you're going around the star, once you get to the top, the north and south poles of the electromagnetic field of, which is based on basically the spin of that star. The top and the bottom of that spin is going to have the least amount of hold on the matter. So as it is pulled towards that spot, it has the least amount of hold on that spot. And in that point, it's all like, nope, I'm out of here. As it just can't, it wouldn't just fling out in a sideways direction. It would fling out straight up. That's what we see happening all the time. We see it happening like all the fucking time. And it's called a quasar. Giant jet streams of electromagnetic charged plasma. It's crazy. I was supposed to be talking about snowflakes? No, I was supposed to be talking about the time. How time works. How do I stop this? Where is the damn... Where's the control bubble? There it is. Wow, I've lived this whole time without a control bubble. It's insane. So we've been going at this for 2 hours. We still haven't figured out how to explain time? Yeah, that's nuts. We're talking about all of cosmos and whatever else and stuff and blah. Everything else except for what the hell is time? Well, time... think about it this way. There are two ways to think about time, right? If you think about Mario, the original Mario had everything that was in front of you constantly be generating based off of what was basically already going to happen anyway, and your motions. And as you interact with the Goomba and whatever else, or the shells, it could be sent off forward into something. But if it's sent off backward, if you go far enough, it's not going to bounce back towards you anymore. It's just going to bounce into oblivion because it actually goes off screen at that point, to a point where there is no longer a wall there and it will no longer come back. So there is that point, and it's like 5 blocks into the depths of the past. Imagine time as everything is processing and iterating, and the only thing that has ever existed is not the past, not the future. It has always been the now. The now is iterating. And that is what is happening. Now, if you were to play the tape of the universe in reverse or something, you can pretend that there was a past. And if you were to somehow play it forward, you can pretend that there was a forward. But my guess is that everything that's happening now has always happened now. It is just now. All of time, all of ever that has ever happened in the past, it is all overwritten by what is happening now. There is no longer a past to go back to. There is no more possible a future to look forward to. There is just a now that is iterating into a future that has yet to be. And that is like saying, if you look at it, it's like saying if you have a pond and you drop a pebble in it and the waves happen and then they stop. Time is like those waves happening and stopping. It happened and it started at a specific point. It moved out and did its own thing, and then it stopped. And you know what? The ripples on that pond changed the entire landscape of space and time for the sake of the water in the pond. And then afterwards, they went back to being stable, and they went back to being stationary, and time had nothing to do with them anymore. They were just flat. So this is what time is. Time is the ripples in the pond. And there is no such thing as the past. Because in the present instant, you are seeing, for example, in the course of all time, we could simply be seeing the first waves coming off of the center ripple of space-time. And eventually, it will all spread out. And it simply just does not stop spreading out. Because out in space, it doesn't stop spreading out because there is literally nothing to stop it. There's nothing to interact with. There are no forces there. There is absolutely nothing. We are just going to keep on attenuating out into space. The drop happened. That was the Big Bang. The ripples are happening and spreading out. That is simply the continuing expansion of the universe. Right? You don't have to think big about... There is no such thing as dark energy that is spreading out the universe. The ripples are just spreading out. The entire thing is just spreading out and attenuating, like ripples on a pond from a single drop. Our universe literally is that. If you think of literally nothing else, then think of the universe and the Big Bang is like the drop hitting the surface tension of the water, the ripples spreading out, and then, yeah, of course, everything looks like it's all spreading out in all directions, but it's all spreading out in all directions from everywhere, from every other point in the universe. Everything is spreading out in all directions from each other, meaning it wasn't just like one drop, it was like 10 to the, I don't care what number, 10 to the 2,000, 10 to the power of 2,000 drops in three-dimensional space, all instantaneously hitting the water, and the spreading out is just happening. But everywhere all at once, all the time, everywhere. That is analogous to what is happening with the expansion of the universe. There is no dark matter forcing it to happen. It's just the shock wave of the original drop hitting the surface tension of the water, which is the space-time, the fabric of space-time itself. That's all. As things move along, you end up with like eddies and flows and crazy other curly cues that are happening all in space-time and whatever else. But time itself isn't dilating. It's all progressing at the same freaking rate everywhere, which is nuts. Even though they say that the universe is spreading out faster and faster as we go along. But the truth is, did you really calculate how fast it was going when you're looking at the farther reaches of outer space, which is the furthest back in time? Because you have to calculate that as like every 1,000-fold that you go further out into space, you're also going 1,000-fold further back in time. Meaning you have to accordion it all. You have to do some squash stretching in your simulation of all time that ever has until you are able to finally like look at what is happening as if a person was actually looking at it all from an outsider's perspective. And then you were like, okay, from this distance, it's spreading out this much. When we go further out back, it's taking 1,000 times longer to spread out this same distance. And we move 1,000 away again into the billions of distance away, and we're looking at something another 1,000 times slower or 1,000 times more motion in the same course of time relative to us. What? So you said relative to us, the light, the light and everything else that's happening, it's like you realize it went from moving a certain distance a billion years ago, and then when we notice it, all of the light that has taken its time to get to us at first it took way out there, further away, it took billions of years to get to us. Then, closer to us, it took only millions of years to get to us. Then it took thousands of years to get to us. Then it took a year to get to us. And from the sun, it takes like 8 minutes to get to us. I saw the most crazy, absolute, insane theory of the universe that, well, if you're looking at life in a magnifying glass at 1,000 zoom, everything seems to be happening instantaneously. But for some reason, this person, this foreign exchange student scientist, could not understand that looking at 1,000 away with distance means you're actually looking into the past also. Because you're not just, you have to realize, light takes a certain amount of time to get to us. Like any bullet, like any ball thrown, like any hand moving across the screen, it takes time for that hand to move across the screen. And the light is pretty much instantaneously moving with the hand. Right? The light is refreshing as fast as it possibly could. You can't even tell as fast with the hand. You might be only seeing it at 30 frames per second, but it's going at like 300,000 frames per second. That's how light's moving. And so we think of that and we're like, okay, light moving at 300,000 frames per second. Once you go a certain distance out into the millions of light years away, it's taking millions of years for that light to get to us. And then when you go to the billions, it's taking 1 billion years for it to get to us. And if time is moving differently based off of gravity, when we look towards the Great Collector, and when we look away into other regions of space, we should expect to see different amounts of time passing. Because at that point, it's billions of whatever the factor is difference between high density areas and regions of space and low. And so if you see something moving towards the Great Attractor at whatever speeds, and the light that's coming back to us from that versus something in the opposite direction, which means there is a direction to space. It's not just all spreading out in the same direction evenly. It's not doing that. Even though there are videos saying it is, it's not. Then you have to, according to that theory, you have to see things moving slowly away, but they're all moving at similar speeds. We all have said in previous videos, other videos, it's all moving at similar speeds. But also there's this Great Attractor thing. And if it's all moving at similar speeds, and yet there is a Great Attractor thing, then that means time dilation is not a thing, because the Great Attractor and the movement of everything and the flow of the thing, we would notice that there is a greater amount of speed with that and things. That, like, the tick of the clock is supposed to either, what is it, tick faster or slower? So that there's more ticks of time for the atomic clock if it's going faster or at a higher amount of gravity well. Right? And to me, it just looks like an object that is going at a crazy speed, and so the atom and the electron and the pulsating of this, what is it, boron? Beryllium? I remember it because it's from Galaxy Quest. Did I say Space Quest? Galaxy Quest. One time I mentioned Space Quest, and it's like, no, not Space Quest, Galaxy Quest. I'm gonna have to go through my comments that I've made in other people's videos and be like, no, I meant Galaxy Quest. You know what I meant. Because I described their version of teleportation, which is not teleportation, but they put you in a pod and they shoot you like a projectile towards the planet. And somehow you land face up, and somehow you land without splatting into a billion pieces. That's fun. But you stay intact the entire time. How the hell do you land and not die? I don't know. You're literally on a missile heading to the planet. You hit the surface and then you're suddenly just there. It's crazy. And you're moving at meters per second when you go hit the planet. You're moving at crazy speeds when you're shot out of the goddamn spaceship. Galaxy Quest. Dude, Tim Allen and all that. Watch it. It's hilarious. Very fun. Dude, the guy who played it's the same guy as in Harry Potter played in that. Warrell Weasley. You know, Snape, the dark-haired dude. You know, the boy who lived. Yeah, the boy who would have evaporated or whatever it is. In like the end of the Fantastic Beasts and whatever. Moving on. Yeah, he played in Galaxy Quest as well. He was the purple alien. Uh, Dude, Rockfrost Hammer will avenge you. Yes. Yes. The Sons of Gorgon or something. Um, I got that. That's wrong. That is so wrong. I'm sorry. I'm not sorry. Tell me in the comments what it is. The Sons of something else, but it's not Gorgon. Tiramath? I don't know. Gilead? Tell me in the comments what it is. What's the phrase? What's the saying? By the sons of Mordor. By the sons of... I don't remember. I will avenge you. And then when he actually says that line with feeling to the guy who's dying, but he's not dying. Spoilers for Galaxy Quest. He's not actually gonna be dead, which is good. And then he goes crazy and just beats up a bunch of people. I will avenge you. He's like so pissed. It's amazing seeing him that pissed. He's like, there was the fake fight scene, and then there was him raging out like a maniac, and it was the most beautiful thing. Yeah, Professor Snape, like, what's his name? Purple-haired, like, eats octopus dude. Mmm. Gotta love your octopus. And then it exploded. Yeah, then it exploded. We are off topic. I'm done. I'm done. I'm having too much fun talking about science. Oh, God. But yeah, they went at crazy speeds, and they went and they did teleportation, which is just you in a tube. Arrow of time. I don't know how to explain arrow of time, except for it is a quantum. Like think of Planck meter. You can go farther than that, and you have time suddenly. Like the smallest possible bullshit. There's no such thing as the smallest possible. You can go farther than a Planck meter. Who cares about physical matter? You can go farther than a Planck meter. Who gives a crap about physical matter? I can make a measurement that's more precise than a Planck meter with a long enough lever. A long enough lever, or a long enough connection of like all those gears that are the gear ratio is 1 to 1 billion and it would take so long to do it. Yeah, that's a Planck level. That's even more accurate than Planck length. You move it 1 inch on the first gear, and the other inch and the other end of the whole thing doesn't even move a Planck length. It doesn't even move a Planck length. It moves a fraction of a Planck length, which is insane. Yeah, the 10-10 gear ratio gear set that people are so fascinated by. It's like, ooh, it would take you so many amazing amount of years, yada years, to move it 1 bit on the last gear. It's like that means that when you move the first one just an inch, that's more accurate than a Planck length on the other end. That's all it takes, really. How many gear? At what gear is the Planck length? Um, 4? Gear 4 probably is my 10 to the 10 to the thousandth. Is that right? Planck length? 4. I'm thinking 4, 3 or 4. An inch equals a Planck length, somewhere around there. I look it up and it's like it's not that. Who cares? We gone from 10. We gone to 10 to the 10th. We've gone to the Google. Whatever. Arrow of time. Um, Scene stealing hack. 42423542 something. That crazy the munchers, crunchers, slammers. I don't know. The Mega 13, the Omega 13. And what did I call it? I called it the Mega 13 when I was able to go from 0 to full speed in 13 seconds in Outrun. I think it was Outrun 2009, where you had a rocket on the back of your car, and to go from 0 to full speed in 13 seconds, or 0 to the rocket boosting was 13 seconds. If you didn't do that, you were 0 to full speed in 19 seconds. It's a whole 5 seconds of sped up that you're not needing to do. You're already full speed. So it's an extra 5 seconds of full speed time. That adds so much more to your full time. I still have that game. I could play it. It's fun. It's not great, but it's fun. Like you have to know exactly what directions you're going right and left. There are secret paths on the sides of it that's weird and stuff, and you can do that, and it's neat, and it has jumps, and there are cars to avoid, and the road has collision, which means it slows you down as you go, or you could actually run into shit and explode. And you're going like 250, 280 using the rocket. It was crazy fast. You were fast. I forget if you were faster with manual than with automatic. One of them was faster, slightly. Their top speed was faster. Anyway, the arrow of time. Yeah, if gravity does not affect time, which it doesn't. True reality, like screw flat earthers, they're stupid. Shut up. They're just fucking stupid. They're just talking out of their ass. Alien believers, they're talking out of their ass. But when I tell you that there's no such thing as time dilation, I'm not talking out of my ass. It's everyone else who's at NASA who is talking out of their goddamn smart asses. It's sad, but it is true because you're just manipulating the clock. You're not manipulating time. When you think about it, if you actually were to try to physically move as fast as you normally would move, you can't do it. Because why? Because the force of you being pulled back into your chair with the G forces, the gravitational forces, force equal to gravity on the planet, times 2, times 5, times 9, times 10, times 13, you're not able to move forward as fast as you would otherwise, blah, blah, blah. And so, crap. So it's not good going faster. It doesn't mean that you have more or less time to experience as you're moving at that speed. There's nothing about that that's real. That is not real. The clock is just being manipulated. Everything else considered, like if you're actually doing chemical reactions and stuff, yeah, you're messing with chemicals with those speeds. You can do that in a centrifuge. You're not manipulating time in a centrifuge. No, you're not. You really are not. No. That's not a thing. The abduction ride is not manipulating time. You're being pulled back towards the back of the... Forget it. I'm done. My phone's gonna die and I don't want to keep going. I ran out of things to say. I don't actually have an answer for the arrow of time, but eventually my battery dies, so eventually you have to charge again. That's the arrow of time in play. The video took this long. That's the arrow of time at play. I don't know how to tell you this. It's not reversible. It's just not. Whatever. Determinism is a lie. It's a very small niche specific to only certain instances situation. It's faulty as crap.